We're going to get started with our talk today. Today we have a very distinguished guest speaker, Professor Andrzej Goscinski, who is visiting us from Deakin University in Australia. And actually, we're lucky because he's here for a conference of which he's chair. And we're just taking advantage of his presence here to entice him over here to give a talk. And Professor Goscinski, for the past several years, has been directing the research of the university in distributed systems and cloud computing. And today he's going to talk to us about something beyond the usual type of cloud computing discussion. Normally, how you can provide software as a service in the cloud for research in biology and medical applications, which I think is a very interesting use of the cloud because those kinds of applications have constraints and demands on the kinds of performance and kinds of computing which are different than the usual business kinds of applications. So that's a very short and sweet introduction to you, Andrzej, but I hope
Thank you.
I captured the essence.
Yes, you have. Stephen, thank you very much for very kind introduction. Thank you. To allow you maybe to understand the situation, Stephen asked me how to pronounce my given name, my family name, because my background is a little bit messy and life has not been so messy. My dad was an American, my mom was Polish. My dad was the third generation American. And because I was born in Poland, I received Polish name. I've been living here in America, in Poland, and we landed by accident in Australia. And after making a decision to go there for 2 years to have my contract requirements fulfilled, we are still there for the last 30 years. So some are saying that this is the 51st state of America. We are saying that we have got a big brother here. So that's the current situation. So that is, I think, the explanation of my names here. I worked in applied computer science. I worked as a theoretician for a good number of years, published papers with a good number of formulae, theorems, and so on. At one stage, I thought maybe it would be good to move towards more real world. Some colleagues, mathematicians, are saying that if number is not real, it's nothing to talk about. However, I believe that being closer to applied computer science allows me to say more about how we can shape up computing. This is the first. The second, I believe that computing is a two-part discipline, and I tried to do that. One is to contribute to computing. It is a very important aspect. And the second, we are like, for example, doctors. And as we know, we see a doctor when we need something. So practically, if there is a problem, that is a normal trip. So I think that that is something which drives my research. Two parts. When talking about here, applied computing or something to develop to make it working better, there was a question I asked myself years ago, and for many years, I think I've been thinking whether I am on a good track. 2 years ago at the conference, this conference I'm just finishing working for, had lucky to have Dr. Dan Reed, at that time Vice President of Microsoft, who is currently serving as Vice President Research at one of the universities. And in his presentation keynote, entitled Clouds from Both Sides New, he said something which is my interpretation, so hopefully he will sign his name underneath here. I will go through this literally here. University researchers should find a research niche because they do not have enough resources, and he emphasized human and financial, to compete against mainstream of research carried out by big companies. And for people working in applied computing, it is very relevant. For any, for example, research group of 5 or 10, they can mount a group of 100 in no time with any number of zeros following a dollar sign and 1. And he was right. So I thought it would be good to still stay closer to a niche which big companies won't be interested because they won't be able to make big money, but is of some interest even to them if developed well. So that is one of those elements of my research I would like to present. I will concentrate today on showing how to use software as a service clouds to support high performance biology and medicine applications. Those colleagues who work in clouds know that high performance computing on clouds is a problem. I'll be trying to present why it is the case. Some are saying that now biology and medicine are front runners, even from the government and company support point of view, financially in particular, why it is so important, and what those people working in those areas would like to have in order to allow them to speed up their research and contribute to, well, build new knowledge or contribute to the existing knowledge in their disciplines. Biology and medicine needs. I know that I am alive. I know that there are genes within me and molecules, but I have got good specialists working on our projects from the area of biology. So if you would be prepared to ask questions about the interpretation of some of those results, please forgive me, I am not able to provide a satisfactory answer. I am responsible for the computing aspects there and how to support them building what frameworks or new technologies in order to allow them to benefit. So if we go for this here, those specialists collect a lot of data, and we know that with the current, I think, trend, and we are talking here about big data, they are generating a lot. The problem is with analysis of that. Many of them are still using their workstations or laptops, and they wait for the outcomes of their analysis for not only days, sometimes weeks. That's the problem they face. Many of them heard about, for example, clusters, high-performance computing, but they are not familiar with that. They are not good programmers, and I don't think that they should be. And they are not system administrators, and in many cases, if you worked when developing some more advanced R application, as you know, it's demanding even to make it running. And I don't think that those specialists working in biology and chemistry and medicine should be involved and should even build their skills in the area of computing. The last, I think, very critical element based on our cooperation and work with those specialists is those specialists would like to use computers in the easiest way. That means using their languages, using those elements they are well familiar with. They're saying, I would like to process, for example, using glass because they know what is the meaning of that application, and they should know where their data is stored. That is as much as they would like to have. They want to get relief from any of those computing details. Practically, we are responsible for. In response, this is one of the projects I am currently involved in, and I will go through this here in detail. We would like to carry out the study into the development of a technology for simplifying the development, exposure, deployment, exposure, access, and customization of high-performance computing science applications in software as a service clouds. So that is the main theme of our project, and I think I'll be trying to address it. Why is it so important? It seems to me that if they would be able to take advantage of high-performance computing resources that can speed up their analysis enormously and that can benefit their disciplines a lot. The second, if, as I stated here, we are going to use here special technology which will be based on clouds, they can have access to those resources in an easy manner. They can have an on demand at reasonable costs. Of course, one can say, and there is a debate, what is cheaper to have your clusters on board or to go for a cloud. I don't want to get involved in this. That it's, I think, the area of economists and how they calculate costs and so on. But that is something you would like to go for. And the main idea is to support our colleagues to discover new knowledge, build new knowledge in biology, medicine, and so on. So this is our main goal. I have to ask that question. Are you fully familiar with clouds? All? So maybe I will pay attention to some elements here because I will be addressing them in a minute. So what is there? We have got a network connecting all those resources, and they are, that is very important, configurable computing resources. They could be rapidly provisioned and released with minimal management. And as you remember, based on the NIST definition, there are three service models, and I will present them briefly, simply to allow me to form a background why we decided to go for software as a service rather than any other cloud model. The first, infrastructure as a service within those models, the deliver of hardware resources as a service, and practically users are granted access to cloud infrastructure through mainly virtual machines. The only trend to avoid virtual machines could be observed when one is talking about high-performance computing, but this is, I think, a small branch. But please note here, there's a reminder that practically those users receive hardware. They now receive, of course, some virtual machines, so it is easier for them to configure machine, but to use them, based on even my experience when trying to do that, one must be not only a good programmer, but also must know a little bit about system administration, which for many of our even computing colleagues could be a problem. The second, more advanced, higher-level abstraction model is platform as a service. In this case, it is provided, I think, a complete machine with some software. However, forms a restriction because you have to stay with what is provided, and you cannot go beyond those machines offered, languages specified. However, in many cases, one said that if he or she wishes to work within a given environment, for example, what Microsoft offers, this is a good model. However, there are major restrictions again. The third model here is software as a service. This came practically from the world of business. And as probably we know, we use, for example, a bank. We don't want to know what is going on behind, despite the fact that we would be happy to know how they are cheating on us and they are getting background. However, for us, the most important thing from the execution, software is there. What we run that software on depends on the amount of money we want to spend, whether we want to have results today or maybe tomorrow and pay less. But the most important thing that the users do not have to talk about installations or running applications. That is provided. And that's the most important feature of that environment. So something like that release the user from any elements which could be described in the terms of hardware, software. They are interested in their applications and data. Public, if we are talking about deployments, public clouds, private clouds, community, for example, for some groups of universities, or hybrid clouds. Why am I paying attention to this? In many cases, some universities set up their private clouds, and sometimes there is a need for more resources. So they are going for support provided by public clouds, and that forms a hybrid cloud. Of course, there are some problems how to make it interoperational, but it is a good opportunity, and I will be also referring to this, what we have tried to do in order to achieve that. Essential characteristics, something which I think is very important when we are reading articles about clouds and what they offer, or what they do not offer, and in particular here on demand. If we are using, as an example, high performance computing application, we know that we depend on that computer center which offers those resources, and we are in a queue. We wait. We cannot say, look, sometimes there is a possibility to pay even for that service and receive results faster, but on average, practically we are waiting. We are forced to wait patiently in a queue. And sometimes, based on scheduling, we could be moved to the end of the queue a number of times. Through the networks, broad access, that is a very important feature which we benefit a lot from. Resource pooling, we can use any resource, which is very important, and that is the most critical element when we try to sell the concept of clouds. Elasticity, it is there. We can go for, even if we are talking about infrastructure as a service, we can go for any solution there. It is driven by mainly money, or maybe sometimes service level agreement, depending on the user requirements and those which are offered, or those resources which are offered by service providers. And measured services, which is very important. This is a completely different model. We pay for what we use, only for what we use. We do not have to be on a contract, which makes, I think, all of us working on special applications which do not run many times, I think a great step ahead. Simply, we are ready for something, we can get it on demand, and we can only pay for what we currently use. So I think that is very good for many colleagues who run many individual experiments. What I said here, it is summarized and shows characteristics of clouds that attract business. As I said, they pay only for that stuff which was consumed. They don't have to pay, and in many cases, some laboratory colleagues working in biology, they don't want to pay for a cluster. Simply are saying, I don't know whether I'll be using it or not. So that is very important. That is interesting for many of those specialists. The required service is always there. So that is interesting. One can say, well, that will be the problem because there are service providers which tries to keep you as a client indefinitely. Now there are trials to avoid that, but it is, in theory, it's a good advantage. Computing provides opportunities to small businesses by giving them access to world-class systems. That is a great advantage, and when we are talking now about even supercomputers going to be offered as part of a cloud, I think it is a major step ahead. And on the other hand, if somebody develops a piece of software, it is very difficult to sell it to the public. Through cloud, it is possible. So it is very attractive, and some of those features are very attractive to researchers who are very narrowly oriented from the whole computing spectrum of any computer center. However, if we go for any of those cloud models, as we know, there is no free lunch. It is some form of paying for them. So what is there? If we go for infrastructure as a service, it is necessary to construct a virtual cluster, to go for compilation deployment of distributed software. Is it demanding? Yes. Many of our even competing colleagues experience some problems with that. So one must be trained, and there is a need for system admin skills. If we look at platforms, and in particular here, platform as a service model, the issue is here that there is some limited access to development tools and languages. It is set up by a company, and if we like it, we go for this. If not, we don't have to do that. But they offer good software. So from this point of view, this is a very good model. The third here, software as a service. This is something which I think is very attractive because users are able to access HPC applications through graphical interfaces. APIs could be developed there and can work for users very well. And that is something which is advantageous in comparison to anything which is based on license. If you want to have a special piece of software running on machines of a computer centers where clients are. So from this point of view, we can see that there is something we could be very attracted to. Simply, there is software which is there. Or if we are those developers, we can make this software available to others. There's another dimension of the most critical importance. What about clouds? Are they as hot as they has been in the last years? Based on this graph, we can see here that currently the situation is, I think, improving, and more companies, and in particular in the last 3 years, move towards clouds very dramatically. And probably those elements I presented as basic features which attract clients or business in particular to clouds is reflected through this. What is also important to remember, and I think we have taken that into consideration when starting our project, it is possible to say that all these classes are being developed and taken over. Okay? However, what is the most important element, that the most popular is software as a service model. That means users want to stay away as much as possible from infrastructure or infrastructures if they are considering more than one service provider. And they don't want to be restricted by software which is offered by those which offer platform as a service. So that is something which I think is of the most crucial importance. If we look at the concerns, because that must be also taken into consideration when talking about clouds, there are some elements, and we have taken that into consideration when starting our project. What are the main reasons for staying away or being cautious about clouds? The main are security concerns. I think that based on my understanding as a person working for a good number of years in distributed systems, they have not been made so much worse by moving towards clouds. Of course, there's virtualization. It is possible through those machines, virtual machines, to pass on additional, or to form additional attacks. But otherwise, the problems are of very similar nature. So I don't think that that is something one could be surprised by when talking that security is slowing down the whole taking over clouds. The second, complexity of integrating with existing IT for companies. Yes, that could be the problem. IBM is good at this, and they are addressing those problems already well. And another is cost is too high, which I couldn't figure out what it is really meant by this. Simply, those costs are not so high, unless somebody is expecting that they will be transferring a lot of data, and we pay for bandwidth a lot. And that is still expensive and is not getting cheaper. And as we know, very many laboratories, for example, which run physics experiments, grab those disks and post them physically. Simply, they cannot afford just those costs if they would be trying to transmit via even the fastest network. And those networks, which are used to form a set of different clouds, are not the fastest. So that would be my explanation of the reason. These are the problems. Now, what I would like to pay attention here to, first, if we look at high performance computers and computing, because I said that that is something expected by our colleagues working in biology, medicine, and so on, the costs are high of computation and storage resources. There is a need for advanced middleware, sophisticated discipline-oriented applications, and knowledgeable programmers and system managers. This is the starting point, and those colleagues who run those applications know that we face them all the time. So this is rather normal. However, there is something which would be good to remember, that clouds have been created for business. What is the meaning of this? Practically, those vendors thought that they will be making big money based on clouds. And they are interested in just those systems, simply that they will generate a lot of money when they release that. On the other hand, if we look at high-performance computing costs a lot to run it, but there are only small companies, not big companies with small production making huge money selling something for hundreds of millions of dollars. But this is not a production that allows the company to say we are surviving well. And what we experienced in particular here when the US government stopped supporting, for example, Cray and other companies, that was a disastrous outcome. So we can see that this is not to make money. It is good to remember that. Another element, if you look at the current high-performance computing on clouds, they are mainly supported by infrastructure as a service cloud model. And for example, here Amazon, with their solutions, additional support there, practically is one of the major, I'll be saying, vendors of those services. Another is now Azure by Microsoft, but it is in a different category. This is the first problem, coming from HPC and partly from clouds. Another problem, the cost of time and time overheads in learning how to prepare high-performance computing clouds. As you probably noticed here, practically the first is this. The same. We have to have the same cost to offer those services. It is a high-performance computing environment. So if we would be going to use provided by somebody else, we can benefit from this. But as a starting point, the cost is high. On top of this, we have got the second component, which is very important if we go just for this model, to properly install and configure applications in the underlying facilities. It is not easy. And again, sorry for maybe repeating this, if you develop your parallel applications and later try to debug it, deploy it, run it, it is a demanding job. So the same is here. Clouds and clusters, which are practically commonly used now to support high-performance computing. What is the conclusion of this very short analysis? If discipline specialists would like to use high performance on clouds, they would be forced to become system administrators and good programmers. As I said before, I do not expect those people to spend 40%, and that is based on the current measurements, how much time those who are forced to do that spend in order to have their applications executed even on clusters. So the overhead is enormously high. Rather than to concentrate on their research in biology and medicine, they learn what practically is the responsibility of us, computing people, and only 60% on average is for biology and chemistry and medicine. So that must be changed, and that was the reason for addressing this problem. In response to these two problems, we thought that rather than to go for clusters and knowing how clouds work, we think that the response is in cloud computing. Here, as we are very well familiar, practically clouds are not designed, with the small exception of additional service, to support high-performance computing. Who can do that? Is the question. Companies do not make money on this, as well as other elements of clouds. What is very interesting, that clouds are more oriented towards high scalability computing rather than high performance computing. Why? Networks are reasonably slow. So we can do that and support this well. This is not supported too well. However, the improvement of communication is such that clouds are being considered as platforms for high-performance computing. This is a very important question coming out of this brief analysis. What kind of high-performance computing applications could be executed on a cloud? And if one carries out an analysis, and that was published just recently, if we look at the following applications here: embarrassingly parallel, MPI plus high latency, and MPI. Until now, high-performance computing on clouds, this could be executed well. Grid, due to its association of a good number of links connected among many clusters, can support the whole spectrum of those applications. If we go for now scalability, embarrassingly parallel applications could be supported very well. So there's advantages. With the current trend to improve communication performance, I think the applications which could be considered, and we look at them and study them, they are just MPI plus high latency and embarrassingly parallel. So that allows us to say that these are the classes of applications we can consider when dealing with high performance applications, science applications on clouds. If there's any question, please go ahead. I will be more than happy to take them and provide an answer. What is interesting, this is what our colleagues from biology chemistry raised many times. This is the cost and time which is needed to learn how to prepare the high-performance application, not only on a high-performance cloud, as I indicated here, but also on a cluster. It is the problem for them. Many of them are not prepared even to learn basic commands which are required to build a simple MPI application, but it is the issue. For them, it is wasting time. And here, the cloud users are presented with a set of virtual and physical servers. For them, again, this is another barrier. They do not want to see it. And to put them together to form a high-performance computing facilities to run their software, many are saying, I can wait even 1 week, but leave me alone and don't force me to spend 1 week to learn it before starting running on your cluster. So that is, I think, a natural approach. And I think that that was the reason for trying to address it. Applications must be properly installed. And we know, based on our experience, we pay the price. If that has not been done properly, the cost is too high. So we have to avoid that. So what can we conclude using this? That if we want to have discipline specialists to use high-performance computing clouds, we are forcing them automatically to become system administrators and good programmers. Unacceptable. As I said before, based on the current study, 40% of time is usually their time needed in order to overcome this problem. So the cost is too high. So we looked at another, I think, piece of their working environment, which I think formed a good learning platform. As maybe you even discussed with your colleagues, there are areas, and in particular biology, medicine, where discipline specialists benefit from web-based software tools or packages. Why? Their interfaces are developed using their language. And that is one of the most attractive elements there. They are easy to use, and practically we can see that there are some which support workflow, access grid resources, and some they are used as portals or scientific gateway, such as Hub Zero. What is the most important observation coming out of this? They appreciate easy-to-use web-based discipline-oriented interfaces. For them is the most critical importance. And we thought that it would be good to take advantage of their lessons and their expectations in this area. I am repeating this again intentionally here, despite the fact that I paid attention to that the highest percentage of clouds used models is software as a service. So what we concluded here, that discipline specialists could benefit most from the execution of their HPC applications if they are exposed as services. We can see that trend is there. So this is easiness, I think it is the main factor, and also accessed through discipline or tool-based interface. So that was the reason for trying to put together software as a service model as execution and lessons learned from tool-oriented or user specialist-oriented interfaces. So that was something which formed the first stage of our major project. At one stage, every one of us is asking a question, am I on a good track? Is it making sense? And here we answered that yes, we are. What was the main confirmation or element we have taken into consideration? Some of our colleagues used this GATE software tool for its simplicity, which has not been supporting well high-performance computing, but its interface was very friendly and offered a good number of libraries there to allow them to take advantage of its richness. What they stated, and they promised to release, I think, the end of the previous year or the beginning of this year, that they will be using here this system and offer it as a cloud service. That was to us a good confirmation that such a huge company and such successful company decided to go for a very similar approach. So we thought that that is indicating directly that we are on a good track. Another which I think we came up with just recently when talking about big data and analytics, practically there are just software tools, how to use them well. And putting together, again, software as a service, huge data, and those analytics, it is just having software as a service cloud or clouds and running all those big data. Of course, one can say, what about those big data and transmission? As we know, we don't want to address that at this stage. It is the problem we have to pay the cost of somehow. But that was the confirmation for us. Research questions we came up to when we finished that analysis. How to make scientists able to deploy software applications in clouds. That is something trying to look from the perspective of those biology, medicine specialists point of view. The second, how to make clouds easy to use for those discipline researchers, in particular to run high-performance computing applications. And the third, how to support the customization and reuse of high-performance applications in clouds. Three basic questions we tried to address, and that practically forms our research scope in this area. So what we decided to go for, to develop a technology that the first automatically creates a virtual machine. Some virtual machines are provided by service providers. There are not too many in the area of science and in particular high-performance computing. But how to do that is even more difficult. The second, the technology allows us to expose an application as a service. Now we are living in the world of services, despite the fact that we are addressing that formally in the last years, despite the fact that we benefited from services for years. A good example is a bank. A bank is providing a service. We go for a haircut. It's a service. So, but now from the software point of view, how to expose an application as a service. Another deploys it on the virtual machine. It is very important. Otherwise, we cannot do that well if we cannot automate this. And finally, how to generate an easy-to-use interface, for example, web form, which is very important because that must be in the language which is understood by those specialists. They do not want to use our language. So what have we done as an initial stage? Stephen, am I still on a good track? Okay, thank you. First problem we noticed, web services which are used to develop services are stateless. In many cases, if you want to model a computer or a cluster, you have to see it as a stateful service. So we solved this problem and we provided a solution to make those web services stateful. The second is discovery. Discovery and selection is the major threshold, and many specialists ask the question, where can I get information about this? For us specialists going, for example, to Amazon, we have got a catalog of some virtual machines and we can select. But it is written again in our language, and it is not a language which is good for those specialists working in other disciplines. So in this case, we decided to go and provide the technology and later prove its practically feasibility, a dynamic broker which is based on attributed names. So in this case, we can go for attributes rather than for anything which, for example, we specified in a partition name if we go for Unix. Another problem, initial problem we had to resolve at the beginning, as we know, high performance computing systems are unaffordable to small and medium research groups and institutions. What we try to do, having our research cluster, we try to expose it as a service. So for that purpose, we use, for example, the outcome of this to make it stateful. So it was possible. We enhance it by providing a broker, and it was possible to have there the whole cluster exposed as a service. And that was the first step in our research. That is illustrated here. This was the first attempt. We've done it, and in particular, I have done it with one of my PhD students at that time, Michael Brock. And you can see here that we developed here based on the hardware and cluster middleware. We used here PaaS model rather than IaaS to avoid the development of the whole middleware. So it was possible to use the operating system of the cluster. We built here very special stateful system which is using WSDL. To maybe colleagues who do not deal with this, WSDL is a language which describes a service. So if we are able to take advantage of this description, we can put additional resources, and in particular those which are changing dynamically as part of the description. And at the end, practically it was possible to go for building an interface from the system point of view for starting, monitoring, and file transferring, compilation, and those operations, hidden from those specialists. And on top of this, that was building application web forms and dynamic broker, which practically stores all those applications and describe using simple attributes. This is summarized here, so I won't be going for details, but it is presented here straightforwardly what we have done. But the next step was more ambitious, and we wanted to generalize this approach. I think that the time is chasing me up here, and even the watch is falling down here. So, but what we have done here, we thought that if we are able to have a high-performance application developed, and that could be done by a discipline specialist with some support or cooperation coming from a good programmer, and deploy that. We are trying to deploy that within this environment, infrastructure as a service, that was used to build application service, generate web form, and practically this as an entity, that means virtual machine of this, and the web form was published to the broker. And of course, accessing was done by the user, who learns from the broker whether the service is provided. The service means that the application he or she wishes to run, and whether that web form is satisfying their requirements, because it's an individual issue here for a researcher of that area. And if yes, it was possible to execute that as a service on a machine which was provided by the service provider. If not, it was necessary having some support from computing people to go through this path and build that and finally publish and make it available to others. So I presented as a great opportunity, which clouds offer if we want to make available something which is used, for example, by 5 or 10 specialists in a given area working, for example, in gene discovery or matching and whatever. So that was the very next stage of our project. This shows an implementation of this, and we have got here practically the following parts. Here, the bottom, as I said before, we use Amazon EC2. In the middle, we build a HPC library, was used to expose and access Amazon services. And the top, that was here using the Galaxy. A Galaxy is a software tool like a package offering different biology, medicine-oriented services. So we put them together here and use the whole part here presented, hidden from the user as part of Galaxy. And that, I think, was very attractive to all those discipline specialists. They are familiar with Galaxy, and they didn't have to go for any details there in order to learn. To show that briefly as an example, here, sorry for the quality of this memory dump here and screen, and you can see here this describes briefly the Galaxy web-based platform. This was done with another coworker of mine, Dr. Wang, and this describes simply the interface which is offered by Galaxy. At this stage, not important what they can do. It is possible to find all those possible services offered by the system. But the next step is more interesting, that through that enhancement based on our, practically in this case, I will call it middleware, which exposes the whole cloud as a service, we're able to build a system where we, based on expectations of our biology colleagues in this case, could specify the number of nodes. They could learn that. Cluster, they could select. Now, what they wanted to run, that was, for example, MPI BLAST. And here, the computer server type, which is very much biology oriented, and that is in their terms, and execute. So practically, based on this simple interface, they were able to define what they wanted to do on what, application, and data. And practically, that was something they were expecting. And here, now we can see that this shows that the following jobs has been successfully added to the queue. In this case, create HPC cluster, and it describes what has been done in order to allow us to offer it to those specialists. Here, we are showing the interface to access just MPI BLAST. And again, this is very specifically defined that we want to have the following type of blast. Those specialists, based on their experience, have got a good number of them they wanted to carry out experiments on. Here, we could specify the number of processes. We link them, and at this stage, this is now prepared in the advisory form, how much they would pay if they would run, for example, on 128 rather than 64 CPUs. So they were able to do that. We have not implemented fully the cost versus the environment, but we could allow them to specify some parameters which are important from their application point of view. And here, practically, it is showing the finished execution. Sorry, I cannot even read it from here. So I'm sorry, but please believe me, it was running, and that was to the satisfaction of those specialists. Now, since I have got 1 minute, I will avoid covering two other case studies, and I will go for the conclusion, so please forgive me that we'll be having some jumps here. Well, this is an example how we have taken advantage of hybrid clouds, and we are doing that successfully using our cloud, which was private cloud on the Deakin cluster, and another cloud created on the Monash University, which is, I think, 80 miles away from our campus. So we are able to use these facilities. In conclusion, because there's more than one, we believe that clouds are being moved from business to specialized research. Not that we are able to run high-performance applications on clouds, that there is the whole technology which allow us to do that and do that efficiently to support those specialists. The second, as we know, on clouds they promise scalability, faster turnaround time, which was enjoyed, well, very enjoyable to our colleagues from biology and chemistry, because we ran those experiments with them. Lower costs, maybe costs were low because that was done on the university machines and they had got grants to cover the cost, so that was probably not counted directly. This is very important to those specialists. They don't have to know anything special about programming. They should know that parallelization can help. So they were able to take advantage, but they were not familiar and do not have to be familiar with system administration, deployment, and so on. The next interface, what we learned from our colleagues, was the most crucial importance. Interfaces were developed to satisfy their requirements, the way they communicate, the terms they use. So that was of the most critical importance. We learned a lot here from web tools because they used to them, so it was necessary to see how they take advantage of those tools. That was the combination we, I think, satisfied their requirements well up. And here, what I would like to say that HPC applications exposed as services of software as a service cloud and access using web forms is the solution. If we want to say that we move towards specialized research. And based on what we also benefited from, that hybrid cloud will grab the HPC market. In many cases, if we go for university environments using our colleagues' environments from other universities, and if that would be offered as a hybrid cloud, would be very beneficial. Thank you very much. If I grab too many minutes, I'm sorry. Thank you. Thank you.
Since we're over time, I'll talk fast to grab back the time. Normally we end by this time, but we continue out in the hallway where there's some soda drinks and cookies and
Yes,
things.
I'm
So
happy to do that.
since we're over time, why don't we just take our questions outside to continue the conversation with Dr. Goscinski right in the hall out here.
Yes. Thank you very much for coming and your attention.